recording. Okay, so this is a demonstration of a up and down, a proton with elliptically polarized photons, where these arrows indicate the axis of polarization. And what we're going to do is we're going to show the superposition of these to a unit vector, which will be like this. So this one is an electron. Now I've got some papers on Phasor which will show the details, but I just wanted to show the actual superposition in 3 dimensions because it's slightly tricky. And what we're doing is we're basing this on Dr. Randall Mills's work, right? So the idea is that the particles are on the surface of a sphere, all right, and darling, that, hold it, go on, hold it. The particles are on a surface of a sphere, and you have the photons go in great circle loops, and the current goes out at right angles at all times around, and it just by a complete because we're using spherical harmonics, by a complete coincidence, beautiful mathematical coincidence, the current circles, or when you integrate them all, they all sum to an equal magnitude. All right. Now each of these elliptically polarized photons is done by taking a right-hand circularly polarized photon on this direction and a left-hand circular one thing, and it sums out now to give an elliptically polarized one at the 45-degree angle. Now where's the 0 point on here? 0, 0, 0. What I've done is I've deliberately I've deliberately done these on a Mobius strip so that you can see it. Now, unlike what Dr. Randall Mills did, these are 2 revolutions, so the axis comes back only after 2 revolutions, just like surprise, an electron which has spin half. All right, so you can see that on the back there. That one is in the opposite direction. All right. So now this is the bit that gets tricky. Where are the 3? Where's me 3? This is my. Yeah, that's my daughter. Hi, sweetie. Okay. So where is the 0 point on here? Right, that's the 0 point. So this is the down quark, and naive. Okay, so we're going to put it on a great circle and leave it there. All right. And this one is the one of the up quarks. And 240. We're looking for the 0 point. There's the 0 point. Now we are naively going to put them on here like this, and this one doesn't really matter. I got it wrong, the arrows and stuff on here, but it doesn't matter. Turn it the right way around. Okay, all right. So when you do a superposition of these 3, you simply do not come out with the unit vector, because you've got a unit vector here in a unit vector in there, the thing. So you've got twice the vector here, and this one, if that's 30 degrees elliptical polarization axis, 30 degrees polarization axis. So sum of those 2 comes out to double the thing, and then this one, which is at 240 degrees, simply does not come back to a unit vector, which is what we want. We want something that comes back to basically exactly the magnitude of the electrons and phase of the electrons elliptical polarization axis. All right.
Yeah.
All right. So here's the bit where it does actually work. What we do is we turn this one through 120, that one through 120, and for time being we're going to leave this one here. All right. So let's take the blue one off. That's the down quark. Now I'll put that down there so I know where to get it back. All right. Now, when we turn these through 120 degrees, he comes out to here, and this one, this is so awkward. Apologise. This one comes out to there. When you sum these two together, something amazing happens. Because it is a 120 degrees, the sum of the two comes out, and you rotated one minus 120 and the one plus 120, it comes out to a unit vector due to the properties of an equilateral triangle, comes out to back where you started, as if you only had the one up quark.
Ooh.
I know, right? So now we have two of these on top of each other. No, that's the electron. Sorry.
Whoops.
Yeah. So now we have two of these. I apologise, I'll just turn this around like that, I think. Okay. But, so the superposition of the two up quarks, because they were turned through 120, come out back to the position of the, that like that. All right. But you can see that the sum of these two vectors is not the same as where's the this is so, come on, where's the 240, 210? The sum is this one. Okay, so what we are going to do is we are going to turn this one upside down so that it's on that it starts from the opposite position on here. All right. So, unfortunately, we have the pieces of
paper.
The paper things. Oh! We went the wrong way. Sorry. It's very important to get the direction right. Probably, actually, we need to rotate the other one. Okay, the other one the other way. Okay, right. Now, look at these two vectors. Alright? This one's minus 30 degrees and that one's 30. The sum of those two vectors comes out to a line on the thing. And in fact, we can take away the ball.
Bye, ball.
Alright. And what we're going to do is going to put these three together like this, okay? So,
I'm a caravan.
the sum of these two vectors comes out to an angle of 0. Now we're going to rotate around.
Rotating.
Alright. And this one here, we have, sorry, I drew it on the completely wrong place, 0, 30, 60. So the sum of these two is still exactly the same point as on an electron. 30, 60, 90. Sum of these two vectors is the same thing. Remember, these are elliptical polarization axes, and we're demonstrating the actual rotation, so the omega t as well here, a thing of a full loop. But basically, you get the point that it doesn't matter at all points on the surface of the sphere. The sum of the three elliptically polarization photon thingamies with equal frequency and magnitude come out sum at all points on the thing. little points to that of a electron. I realise it's not a photon. That should be a positron. We're talking about a proton. So I've probably got things. I should have rotated something around one way or the other, etc., etc. Now, one other thing I should point out is that what I've deliberately done is all of those Mobius strips there should have been offset by 45 degrees, but for convenience I didn't add that on because it's just the numbers is just difficult to explain. If you look in Dr. Randall Mill's book, the right circularly polarized photon is superimposed with the left circularly polarized one, and you get an elliptical polarization axis for the electron of 45 degrees with 1 over root 2 over root 2 magnitude, which is then scaled down. If it was on 0, you would end up with the elliptical polarization axis would be 0, and that would be a circularly polarized photon. So it wouldn't be. It would be yes. So, but by having them at all at 45 degrees, and then having plus another 30 for the up quark and minus 120 for the down quark, you end up always with an elliptical polarization axis. And basically what it is that the difference between the electron and the other ones is that we're starting from the z-axis upright position, the phase starts at 0 for the sum of the things, but for the right circularly polarized and the left polarized, so a thing for the two superpositions to give you the one at the 45 degrees. But for the up quark, you start. The 0 point, the upright point, is here, 30 degrees off. All right, such that when they sum, you end up with that the representation of the arrow that I gave, which was at offset by 30 degrees to indicate that. Okay, so yeah, it actually works. We have a demonstration of elliptical polarization superposition coming out to unit vector, based on 3 quarks, by one of them being the one up quark being here, one up quark being there, and the down quark being on this line. But because the phase is half that of the rotation, but that gives you the spin half, the down quark is rotated through 180, but the phase angle, the phase only gets rotated by 90. So despite the fact that the down quark is at the minus 120 position and the up quark is at the 30, the because of the spin half, the down quark, when it is moved on the surface of the ball by 180 degrees, the phase actually goes through 90, and that's how you get the two summing always to the right point on the unit vector, which is where we need it to be. Just a reminder that the two up quarks, because they are symmetrically, one is rotated 120 minus 120, and the other one is rotated plus 120. The superposition of those two comes out to exactly the same line as the one that the up quark, the down quark is on. And what is very, very interesting is that they are on diametrically opposed points on the ball. So the photon's position, the superposition of the up quarks is here, and the position of the down quark is on the opposite side of the sphere. So That's all. Thank you very much. Thank you. You can have your ball back
Yay,
now.
thank you. Bye.
Bye.